For today's video, we'll be talking about acid catalyzed hydration of alkynes. So for this, we have an example of an R group connected to a triple bond, an alkyne, and this is foregoing a reaction of H2SO4 and also comma HgSO4 all over water. Right. So when you see this reagent, always think of acid catalyzed hydration. Okay. And so for this, we would get a reaction, breaking that pi bond and making it into a double bond. So triple bond going into an double bond. So an alkyne going to an alkene. So we put the carbon over here, and then the OH would be on top of here. Okay. And so for this, this is called Markovnikov, right? This is Markovnikov because OH is on the carbon that has the most substituents. Okay. And this carbon is a secondary carbon, right? This over here, because it's connected to two carbon groups, and whereas this carbon is a primary carbon, which is connected to only one carbon. So that's why the OH would go on top of here with a single bond. Now from here, we have something called, right here, this structure right here, when we have a carbon double bond with another carbon attached to a alcohol group. This is called enol, right? Oops. It's called enol. Okay, enol for alkene, ene, and ol for alcohol. So this part right here is enol. Enol is not very stable, so that's why we go a process called tautomerism. And so from this, we would get something called a ketone, a functional group ketone, right? So this is called ketone over here. Okay. So basically, this is called ketone enol tautomerism, which takes place. So as you can see, the H over here was over here, but now it's back over here, okay? And we know that the double bond was over here, and now it replaces it over here. So basically, you can just draw from the reactants, you can just draw it becoming an enol, okay? So a carbon double bond connected to an OH group, and then from there, you can automatically turn it into a ketone, a functional group ketone like this. So let's try another example. If we have this structure right here, okay? Now this is called terminal, right? Because it is the triple bond is on the terminal side. So our last example, this was called terminal because the triple bond was on at the end of the group, right? This is at the end, and so that's why it's called terminal. So from this, we react with the same reagents that we used before, H2SO4 and also HgSO4. The HgSO4 is just, it's just there, okay? And now this is also reacting all over water. So from here, we do the same thing, redraw the structure, right? So before that, we should count the carbons that we have. So we have 1, 2, 3, 4, 5. So we should always have 5 carbons, okay? So 1, 2, 3, 4, 5. Right. The double bond will go over here because that's where it's on the terminal side, and the OH would go on the carbon that has no substituents, so over here. So from this, we see again we have something called an enol, right? Alkene connected to an alcohol group. This would go something called tautomerism, which where we change the double bond and the hydrogen. So we would get something like this, make it into a ketone because it is more stable than an enol, having an enol. So this is our final product. So this right here is our major product, and we can call this as our minor product. So that is it. Let's try another example. If we have this structure over here, okay, again we have a terminal alkyne because it's at the end, and so this was reacting with the same reagents that we used before, and so we would have redraw the structure, okay. We would form an enol again, okay. We have the enol, right, double carbon connected to that alcohol group, and goes a process called tautomerism. So we redraw the structure, trying to make it into a ketone, okay. So acid catalyzed hydration will always become a ketone. Double bond on the oxygen, and then we have the hydrogen sticking out. You don't have to draw the hydrogen, but I always assume it's always there. Okay. Let's try another example. Again, of this, for this, we're still in acid catalyzed hydration, so we still use the same reagents, H2, SO4, with also comma with HgSO4 all over water. Right. So from here, we should count how much of carbons there is. So there's 1, 2, 3, 4, 5, 6, 7, and 8 carbons in total. So that means we would have 8 carbons in total again. Let's look at this. If we drew a line right directly down the triple bond, we see that this side over here, this side over here is exactly the same side as this. So this is called, it has internal symmetry. So it's symmetrical. Both sides are the same. So we would have one product, okay? I'll show you. Redraw the structure. So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons, okay? Now, the triple bond was between 4 and 5, carbon 4 and 5, so make that into a double bond. And so if we look at the numbering of the substituents of the carbons, carbon 5 over here is secondary, but also carbon 4 over here is also secondary. Okay, so they're both the same, and this is a Markovnikov rule where the OH would go on the carbon that has the most amount of substituents, but in this case, they both have the same amount of substituents, so it doesn't matter where you put the OH, the alcohol. So I'm going to put it over here, okay? Okay, but some of y'all might put it over here in the bottom portion of it, and then say that these two are enantiomers. Again, the structure has symmetry, so there can only be one product, and so that therefore you can either draw this alone, or you can draw this alone, but you can't have both of them. So you could just pick one from here. So I'll just pick the top one, and so from here it'll go into tautomerism and draw a ketone. So redraw the structure. Now the OH will go away and form an oxygen over here, and there we go. We have a ketone. You can draw the hydrogen if you want. It doesn't matter. And so for our major product, our final answer would be this. Let's try one more example for the product. If we have this structure, and it's reacting with the same reagents, H2SO4, HgSO4, and so to draw it into an enol form first got to count the carbons. We have 1, 2, 3, 4, and 5 carbons. So we redraw the structure, 3, 4, 5. From here, we see that if we cut down the triple bond, you don't have symmetry, right? This side and this side are two different sides. So that means we can draw it two different ways. So the triple bond was between 3 and 4. So that will be over here. That means we'd have an OH group over here. Plus, it's an enantiomer, right? Coming over here. Okay, so these are both two of the options that you can use. So they both have two major products, right? We redraw the structure, molecule, and then all we do would just draw a ketone, right? And the hydrogen sticking out. And for this, we would have redraw it again and have, oops, well, messed that up. Okay, we have the ketone coming from here, the hydrogen from here, and then for the bottom one, would have the oxygen coming from here and the hydrogen coming from here. And so for this product, this reaction, we would have two products instead of one, and they all form ketone. Okay, this is because there's no symmetry, and we had an option of adding both of them carbons, because the carbon over here was a secondary carbon, and also the carbon over here is secondary, so we can either go left and right, but in this case there was no symmetry, so that's why we have two products. Okay, they're both secondary carbons, and therefore we have a total of two products plus. Now let us draw the mechanism for these. So for this, if we start with our first structure, we have a terminal alkyne. First things first for this, actually no, we don't start with the terminal alkyne. We start with the enol, right? The enol. Again, enol is this carbon is connected a double bond with the carbon over here and connected to an alcohol. Okay, so this part right here is the enol. We start with the enol. And this oxygen has two lone pairs. We bring out H3O plus, right? Because this is an acid catalyzed hydration. This has one lone pair and a positive charge. So from here, the mechanism for this, there's many mechanisms for acid catalyzed hydration, but this will be the simple form of drawing its mechanism. So this lone pair from OH would go and form a double bond. Well, this pi bond will grab this hydrogen and give off its electrons to oxygen. Will make a reactant of having a double bond on that OH, which has one lone pair with a positive charge. What we formed with that H3O was water. So to remove that positive charge, all we do is grab that hydrogen, and that hydrogen gives off the electrons to oxygen, which will give us a reaction of only having an oxygen on here, and that hydrogen was grabbed, put them over here, and so this is our final product for this mechanism. Also, going back to that last problem, we have the final mechanism as this, but it is also with H3O plus that we had made. So this, in fact, is our final answer for that structure. Okay, so we started with the enol, right? So might ask where I got this structure from. So we had this original structure, an alkyne, and it was reacted with the H2SO4, comma our HgSO4, okay, and this is all over water. So these are our reagents for this, and so redrawing the molecule, we would have an enol, right? This part right here is our enol, and this is the part where we start with the mechanism, right? So we started with this. This is where we had started the mechanism, drawing its mechanism, and going to our final answer, which was this. Let's try another example, but to draw its mechanism, we always start with the enol portion of it. Enol portion. So, for example, if we had this, right, this alkyne, and this is reacting with the same reagent, so this would be H2SO4, comma HgSO4, and it's also reacting with water, right? And so we would make the enol portion of it, make this into a double bond, an alkene, and have the OH on top, right? So this is the part where we want to start with the mechanism. So from this, we would have this with oxygen having two lone pairs. Okay. So from here, we would have the H3O plus would come in, positive charge on that. One of the lone pairs of oxygen will form a double bond here, and then this double bond will grab that hydrogen, and this electron will give off two oxygen. And so from this, we would get a result of this. Okay, and this oxygen has one lone pair with a positive charge, and that hydrogen, you don't have to draw it, but know it's there. Okay, it does make sense because this carbon is a primary carbon, right? Meaning it's only connected to one other carbon. Okay, that is, it has the least amount of substituents, and this is Markovnikov, so that's why the hydrogen will belong there. So from here, we would have the water that we had made come in. It's one of the reagents, and it will remove that positive charge. So it grabs that hydrogen, and so this will remove that oxygen, giving that oxygen a two lone pairs. So for our final answer, we would have the ketone that will be made, right? The ketone, right, has two lone pairs. There's a ketone, but also the H3O plus that we had also made. And this is our final answer. Let's try another one. And so for this, we would use our other example, right? So this would react with the same reagents that we had been using, H2SO4, HgSO4, all over water. This will give us a product of this, making into a alkene. So we put the double one over here because this carbon is carbon number 4 and this is number 5, so that's where the double one will go. So from here, you can either have the OH sticking over here, or you can have the OH sticking over here, but you can't have both because, again, this molecule, it has symmetry. The left side and the right side looks alike, so there will only be one final product for this. So for this, I'll pick this side. Oxygen has two lone pairs. We also have the hydronium ion coming in. So this is connected to H3O plus is coming. Positive charge. Again, we do the same thing. Lone pairs of oxygen goes and form a double bond. This double bond here grabs that hydrogen. The electrons of the hydrogen gives off two oxygen. We would get a product of forming a double bond over here. This oxygen has one lone pair with a positive charge, and we have the hydrogen over here. You don't have to draw it, but assume it's always there. Our goal is to make ketone, so from this, we got to remove that positive charge and draw that water that we had made. Okay, one of the lone pairs of oxygen goes to hydrogen. This electron will give off two oxygen, will give us a final product of forming a double bond over here, two lone pairs, and we have the hydrogen on this side, plus the H3O plus that we had made. And this is our final answer for this mechanism of this product. Try one more example. So we see this is an internal alkyne. We draw down the line of symmetry, and there is no symmetry because the left side and the right side does not look alike. Therefore, this will have, it might have actually two products, but we'll see. So this is reacting with the same product that we had been saying lately, H2SO4, HgSO4, and all over water. Okay, redraw that product, the structure. So it has 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. Carbons between 3 and 4, so it'd go over here. And so now we determine where does the carbon go. The OH group, this carbon is a secondary carbon, which this carbon over here is also a secondary carbon. So they both have the same amount of substituents. and this structure is not symmetrical. So this means we'll have two products, and they would also have two mechanisms, but we will draw one mechanism and then draw its enantiomer. So I'm just going to pick the OH coming off from here. Now the hydronium ion comes in with the one lone pair, has a positive charge. This oxygen takes one lone pair and makes it a double bond over here. This double bond goes and grabs that hydrogen, and this hydrogen lone pair gives off to this oxygen, which will form a reactant of this oxygen having two lone pairs. Actually, no, one lone pair with a positive charge. The hydrogen is over here. From here, we'll draw the water that we had made. So to remove that positive charge, an oxygen lone pair would go to hydrogen, and the hydrogen electrons would go to that oxygen, which will give us a reaction of final product of making a ketone, but also that H3O plus that we had made. And so this is our final mechanism, our final product, but also we would have the other version of it, this enantiomer of this and plus H3O plus. Right, so both of these are the answer to this mechanism, to this product, but we only had drew only one mechanism, but this is an enantiomer of it, so you can say plus.